Okay, so let's get started. Just a bit of a refresh from yesterday's session with Andreas. He introduced a bit the problem. He introduced this formula of MDPs. And we looked more into the value function estimation. So for a given policy, how can I estimate the value of that policy? He also talked a bit about function approximation. So in the case that we cannot store all the value function on memory because it's just too expensive, all the number of possible states is huge, then we are required to use some approximation techniques like function approximation, as he was also introducing. And for today, the outline will be different. Now we don't want just to compute the value of a policy, but we want to compute the optimal control. And we want to do it in a model-free way. And this means that I want to have an agent, put it in an environment, in an MDP that is unknown, and I want it to try to maximize the expected cumulative reward without knowing anything a priori from the environment. So you have seen these techniques before using in the dynamic programming course, I guess, but in that case, you knew the model was known to the agent, and you could also traverse all the states and actions without any problems of space. In this case, we will see that once we start to make this type of approximations, then a fundamental thing will come up, which is the problem of exploration and exploitation. So I will talk a bit about that in the beginning. And then I will focus in a dimension that separates two types of methods, the so-called on-policy methods and the off-policy methods. And we will see two very well-known examples of algorithms for each of these two classes. Okay. So let's start introducing what is this dilemma between exploration and exploitation. So this is a fundamental trade-off in reinforcement learning. You probably have heard about it. And the idea is that if you choose always what you think is the best action, that's not good. Okay? And that is because you might be wrong, and then you will be wrong forever. So if you didn't explore some of the states and actions that are more promising to your current policy, then you will miss some parts of the states and action space that will lead you to higher cumulative reward, and you can get stuck in this type of local minima. So one needs to find the best action. You need to explore. You need to explore all possible states and all possible actions. But if you only explore, this is not good either, because if you just act randomly, you might not learn anything from the environment. So there's an intrinsic trade-off, and this is what actually defines what is a reinforcement learning problem. Without this type of trade-off, then the problem would be trivial. Okay, so what is the right balance? How to balance the frequency of exploring actions that are random, that try things, and exploiting actions, those actions that are greedy with respect to your knowledge of the environment. So I will just mention some ways of dealing with this trade-off. There's a lot of literature about that. So I won't go into details of all these theoretical results. I will just give you some techniques which empirically perform very well, and which in practice what most people use. So in order to illustrate this trade-off, a good framework is that of the multi-armed bandit problem. So in this type of problems, at each time step, you are faced with k choices. Okay, so imagine the typical scenario where you go to a casino, you have all these slot machines, and you want to pull. Each action is an arm, and you want to maximize your expected reward. So you want to pull a slot machine, and you get some reward. But you can do it in another one, you get a different reward. And in the end, you want to maximize your expected reward. So notice that this is a degenerate case of the MDPs that we were looking at yesterday, in which we have different states. And in this case, we can consider these multi-armed bandit problems as MDPs with a single state. So let's start with the first techniques. So I guess you probably have heard about Epsilon greedy. So in this case, this is a very simple strategy. You fix Epsilon, which is a very small number, and then you choose randomly an action with probability Epsilon, a random action, and then you are greedy. You choose the action that you think is best otherwise, with probability 1 minus Epsilon. So this chooses equally among all actions. It's an extremely simple strategy, but it surprisingly works very well in practice, and is what many people use in practical scenarios. You can be a bit more advanced, and then you can consider the relative importance of your different actions. So imagine that you have a value for each of the actions. Let's call this value Q. And then you can do what is called Boltzmann exploration. So instead of performing totally random with probability epsilon, you can choose actions according to this distribution, right? So this is called Boltzmann distribution. And here we have this parameter beta, which is going to control how greedy we are. So if we take beta to infinity, we're going to be purely random strategy. And if we take in the other side of the spectrum, we will be fully greedy. Okay, so this is another way of dealing with this type of trade-off. The question is, can we do better than this? So do you think that, can we do better? Do you know about other strategies? Any ideas? Maybe it's, you're too tired. Sorry. Okay, now think of it about this in the following way, right? In epsilon greedy, we treat all preferences uniformly. And in the soft math policy exploration, what we do is we consider the relative value of each of the actions. So we can also take into consideration their uncertainties, okay? And this is the idea underlying this optimism in the face of uncertainty. So in this case, what we do is to select among non-greedy actions by taking into account the estimated values and also their uncertainties. So for those actions that I didn't try enough, I will tend to explore more. Okay. And this is actually how this works. So we have to keep the number of times that an action was selected so far. So this is this n at time t. And then for some value c, and this will determine this trade-off, which is usually taken within the range of values of the action. Then we choose the action that maximizes this number, this quantity. So this is the value of the action, and then we have here this term that you can see that the more I increase the number of times that action was selected, the smaller it becomes, right? So the more I know about an action, the less I will use it in the future if it gives me a low reward. And in other words, those actions that were not taken in the past will have large uncertainty and will be pushed up as time evolves. So these are three possible ways of dealing with this trade-off. And now so this is just using this idea of this model, this framework of multi-armed bandits. In the general NDP setting, where we talk about reinforcement learning, we will consider only for the moment the epsilon greedy strategy. But these ideas extend, well, some of them to the more general case. So let's talk now a bit about this dichotomy between on-policy methods and off-policy methods. And for that, we need to refresh some things that Anders presented yesterday, some things that you already saw in the previous lecture. So remember that these two definitions, the value function, so this is a function that assigns to each state a value, and it is an expected value of the future rewards or the returns. And then we similarly define an action value function. In this case, so we assume for the moment that we can store these values on a table. So we can define also the action value function, and in this case we have entries for each state and each action. Okay, so we can see that the action value function is defined in terms of the value function. And then what we saw yesterday is possible ways to evaluate the value of a policy, evaluate a policy. And Anders was presenting this recursion that you could solve with the power iteration method to compute the value of a given policy. So for given policy pi, at iteration k plus 1, I can define the value for a given state recursively using this type of Bellman operator. So far, so good. We have this idea that you also saw probably in the first course about dynamic programming. So there's this theorem, the policy improvement theorem, and this allows us to define a very naive way to improve our policy, to compute the optimal policy. And this tells us basically that given two deterministic policies, pi and pi prime, such that for each state, we have this condition. So the Q value of the policy pi using the other policy pi prime, if the value function of the original policy is bigger, so the policy is greater or equal, then pi prime, which is this other policy, must be as good as or better than pi. Okay. And using this policy theorem, we can define this algorithm called policy iteration, which is actually recursively computing the optimal policy. And that is based actually on greedy updates of our current policy. So we have a given policy pi, we can make greedy updates of the policy by taking the value of that policy and then iterate that until convergence. So we can show that this will converge to the optimal policy and the optimal value function. Okay. So we can see that this is a procedure that alternates 2 steps, right? In one step, we do a policy evaluation, which brings us from here to here. So for a given policy, we compute the value of that policy. And then a step of policy improvement, which brings us from here to here. And this step is done greedily. So we know that at the end, for the optimal value function, V star, the optimal policy will be greedy with respect to that value, and we can ensure that there's this convergence. Now, in practice, we don't need to fully iterate and evaluate the policy entirely, because maybe it's not necessary. We want to do it only for those regions of the state space that are interesting for the task that we are solving. And it might be inefficient to wait enough to get the whole value of the policy. And we can alternate these 2 types of processes at different scales. Okay, so in the generalized policy iteration, we perform asynchronous updates of evaluating the policy and optimizing greedily with respect to the policy that we have evaluated. So what I will do now is to basically present this type of dichotomy, this type of separation between on and off policy learning. And the idea behind this is that they all use different techniques for performing these two steps in different ways. So when we talk about on policy learning, this is the type of policy improvement in which you learn and improve the policy by experiencing from the same policy. So think of it as you're searching, for example, for a goal, and then the policy that you use to select your actions is the one that you're going to learn and improve. Okay, this is a very natural way of thinking about a problem. And then there are these other methods, which are called off-policy methods, in which you are not interested in learning or improving about the policy that you are using to sample from your state space and action space. This so-called behavioral policy is going to be used to learn and improve about another policy. And this another policy might be, for example, the optimal policy that you want to find, or it can be a different policy that is related to other tasks. So this is what makes maybe off-policy learning most powerful. So now I will focus more on the on-policy setting, and we will see some examples of algorithms about that. So the idea is to continue with the line of thought that Anders presented yesterday. So first we will consider all this, let's say, Monte Carlo, where we perform trajectories, we sample the trajectories, and then at the end of the episode, we perform a full update. And then from that, we will apply all these temporal difference techniques and end up with an algorithm which is really applicable into real problems. So the simplest case, Monte Carlo methods, these are episodic based. So this is, imagine that the agent is in an environment, and then it has some policy, the behavioral policy that is trying to learn and optimize. So here the idea is that we perform a rollout, a full trajectory, and at the end of this trajectory, we're going to update the policy or use it to make our updates. And the first idea here is that if we want to do model-free reinforcement learning in the sense that we don't need a model, we cannot do that if we only consider the value function. Okay, so if you remember that the value function was a function that was assigning at each state a given value, if we want to be model free, how is it possible that we can represent our choices, our policies by using only the state value function? So if we want to perform these greedy policy updates in a model-free setting, we will need to use action value functions. Okay, so is that clear? That we really need to do that. So in this case, instead of having a table of the size of the state, we will have a bigger table, which is QSA. But in this way, we can be model-free. So we can store here in these Q values implicitly what is the policy that we are taking by looking at the different entries for a given state, what are the values for different actions. Okay. So this is a bit the idea, no, of generalized policy iterations. We start with an initial policy, pi0, and then we perform an evaluation step. In the simplest case, we do full evaluation of the policy, and then we end up with a new Q action value function that we greedily improve by taking the maximum, and then we iterate this until we converge. So this is the idea. So what are the problems here? Well, if we do this type of Monte Carlo sampling, it might be that we don't reach the interesting parts of the state and action space that are required to find the optimal policy. So we can show that this converges to the optimal policy if we have some assumptions. Okay. So in the case of random exploring stats, we can apply here the policy iteration, policy improvement theorem, and show that indeed at each iteration you are improving your policy. Right. So this is just direct application of the policy improvement theorem. But you have to see that we really need to this assumption that we are starting at different states and actions randomly. So this would be an initial algorithm that assumes this notion of exploring starts. So this is a Monte Carlo with random initial exploration. And this is how it looks like. So we start with arbitrary values for the action value function and some arbitrary policy. Initial policy, random. And we're going to update all our Q values as we interact with the environment. So we're going to generate an episode starting from this initial and action state and following policy pi. And for each pair of state and action, then we will compute the return, which is the sample contribution to our estimate. Okay. And this, well, so far until this line, this is what you saw yesterday, right? This is policy evaluation. But now we're going to take this policy improvement step. So for our current estimate of the Q value, we're going to be greedy and we will update the policy. And this is shown to converge because if we start randomly at any initial position, we can guarantee that the interesting part of the action state space is going to be visited. Okay. So for example, in the example of yesterday, of the blackjack, if you remember that you were doing this policy evaluation using TD0. So if we iterate this type of Monte Carlo updates, we can find the optimal policy. Right? So here the assumption of random exploring starts is not an issue because we start with an initial state is our shuffle deck, so this is not a problem. And this is the type of policy that we find. So you have to see this as so this is our first card, whether we have a usable ace or not. And this is the value of the dealer in the x-axis. And then as a function of the sum of the cards that you have, you need to perform these two actions, right? Or hit or stick. And this is the optimal value function. So you can see that the optimal policy, well, if you have a usable age in the beginning, you will mostly hit. And in the case of not having a usable age, then it depends on what the dealer has, and the dependence is in this way. Okay, so we have defined now an algorithm that it works for these cases, for this simple example, but in general we want to be more ambitious. So let's try to alleviate this assumption of random exploring starts. So what do you think that is a possible option here to get rid of this assumption of random exploring initially? Any ideas? I talk a bit about this trade-off between exploration and exploitation. So instead of saying, okay, I'm going to initially start at every possible action state, well, the mechanism here is to incorporate the exploration in the policy. Right? If I make my policy instead of deterministic, make a stochastic policy that will explore with some probability, then I can show that all action state spaces, all the parts of my action state space will be visited. And in particular, there is this notion of greedy in the limit of infinite exploration, or GLIE, which actually states the conditions that we need for a policy or for an algorithm to converge to the optimal policy. So on one hand, we need to ensure that all state action pairs are explored infinitely many times. So this is given by this condition, where n is the number of times that we visit this pair of state action. So if we wait enough, all the pair action state pairs will be visited. And then that the policy converges to a greedy policy. So this second option is required by the Bellman equation. Now remember that although our behavior policy might not be greedy, because we need to explore, in the limit we know that the optimal policy needs to be greedy. And in particular, it needs to be greedy with respect to the optimal value function. So we have to make sure that the policy, the behavior policy, converges to a greedy policy. And this is the idea behind this condition. Okay. So this is just the identity indicator function that is evaluated to 1 when action A corresponds to the maximum, to the argmax of the Q value. Okay. So if in the limit we are greedy with respect to our behavior policy, then this thing is ensured to converge. So any questions? Now we have removed this assumption of the, so this is an example. How can we make this procedure? So we can take epsilon decreased with 1 over k, where k is the iteration number. So we have gotten rid now of this assumption of exploring starts, and in particular, this is a very simple algorithm called GLIE Monte Carlo control, and it will work as follows. Now we don't need to start at any random state action in the beginning. We just incorporated this exploration in the policy. So this is the idea. In the first step, we sample our entire episode using our behavior policy, which is pi. It needs to be an epsilon greedy, for example, or some soft greedy exploration policy. And then for each visited state and action, we're going to update the number of times we visited that pair, and we will do some incremental update of the Q value function according to this formula. So this is just telling me that this expected future reward is going to be updated incrementally. Right. So notice here that this G is the return that we observe at the end of the episode. And once we have updated our policy, so far here is just policy evaluation, then we improve the policy again, okay, by making it greedy. So now we have a method that is actually applicable into more realistic problems. We still require to store all state action pairs, which this might be unfeasible in real scenarios, but it is shown to converge to the optimal value function, and then it is shown to produce the optimal policy. So is this clear? Notice here that this what we are doing here is an incremental update of the expected value, but this is guided by our behavioral policy. So we are not taking independent and identically distributed samples of Q. So our policy is changing the samples that we take, and these samples that we take are used in turn to change our policy. So this is more sophisticated than just take some average. And this is the idea of on-policy learning. Okay, so now the picture is slightly changed. We don't need to do a full evaluation step of the policy, so we don't need to go up to the top. We can just roll a single episode and then perform updates once the episode is finished, okay, as the algorithm was saying. So the policy evaluation is actually a Monte Carlo policy evaluation step where we approximate the Q function by our fresh latest value. Okay, we don't need to wait until we evaluate the whole policy. We can just use our Q values as they are being updated. And in the policy improvement step, we use an exploratory epsilon greedy policy. So is this clear, the difference between this picture and the previous one? Now notice before we were doing a full evaluation step, and in this case we just evaluate a bit with using the sample episode that we just run, and then we act greedily with respect to that policy, and we iterate that. And because we will explore all the action states end states infinitely often, and we will become more and more greedy as this procedure evolves. We will guarantee to converge to the optimal policy. Okay, so can we do better? What is the problem with this? So we solved this problem that we needed to explore. We needed this trade-off between exploration and exploitation. We solved this problem also that we need to be model-free, and this we solve by using action value functions. Are there any ways to improve on that? Any guesses? So remember that now we are performing a full episode, and after the episode is finished, we can update everything. Maybe it's more efficient if we can do our updates per time step. So instead of waiting until the end of the episode, we update at each time step. And this is the notion of bootstrapping, okay, that you saw yesterday for evaluating a policy. So this is a key idea underlying both dynamic programming and all TD methods. And the idea is what you already know. So instead of updating an estimate from the true value, then we use the same estimate at the next time step to update your current estimate. So we make a guess from a guess. Okay, and we can think of this type of technique in two settings. No? When we're trying to evaluate a policy for a given policy pi. So remember that this is just the definition of state action function, which is this expectation. And remember that we had this cumulative sum of rewards for starting a given state S and action and applying policy pi until the end. Now we can replace, for example, all this sum here by what we know already. So this is this q pi here. Okay. And this is the idea of bootstrapping. No? In the case of using just the next step, we talk about TD0, but we can generalize this to a more general setting. So this is the case for the Bellman expectation equation. We just replace our estimate by the next prediction. But we can do the same with the optimality. So instead of taking the values that we visit, we can use the maximum. Okay, so this is our current maximum of our current estimate. Okay. So these two equations will give us actually two different methods for solving this type of reinforcement learning, and as we will see later. So the first one is this so-called SARSA algorithm that in the tabular case where we can store all state action pairs. So it's very simple here. We just look ahead of the next state, an action pair, and we update our Q values based on that. Right? So this is basically the idea. This can be a trajectory that we sample. So we are on state at time t, then we apply action at time t, we get some reward, and we go to a new state. So think of these nodes as being state action pairs, which are the entries of your table. And well, this is called SARSA. As if you look here, then we have SA, RSA. So in order to perform the update, you will need to have these state action pairs at time t, and then the state action pairs at time t plus 1 plus the reward that you get at time t plus 1. So this is also another way of illustrating this type of backup scheme. So we look ahead one time step, and then we perform this update. So this is the very simple SARSA algorithm. And we start by initializing the state action function arbitrarily. Then we choose an action AT, for example, using our Epsilon greedy. We could use another exploratory policy. And we observe the reward at time t plus 1 and the new state. We take a new action, and this is our update. Okay, so notice here that we are performing, again, incremental updates of Q. And our new target is going to be defined by our current estimate of the Q value at the next time step. So this is the thing that we want to minimize. This is the temporal difference error. And something we can do is to reduce the size step over time, so that as we are iterating, this TD error is less relevant. Okay. So this you actually need in theory. So you can show that the SARSA algorithm converges to the optimal action value function under the following conditions. So the first condition is if you use a grid in the limit of infinite exploration sequence of policy, as we saw before, and you use this type of updates for the step sizes. So you decrease alpha, let's say, properly. So if you take the sum of alphas, it's infinite, but it decays with this condition. So this also, you saw yesterday when Anders was explaining these temporal difference methods. What happens in practice is that SARSA works well even if you don't decrease alpha. So this is to show theoretically that the algorithm converges to the optimal policy, but many times in practice the convergence of these on-policy algorithms is very good. So you don't need to decrease alpha in those cases. Okay, so let's go back to the generalized policy iteration scheme. And now, instead of having full rollouts where we update after one episode, what we do is to update at each time step. Okay, so we alternate these two processes of policy evaluation at every single time step. Okay. Is there any question about this? You can see the difference between these Monte Carlo updates where you update everything when you finish the episode and these TD updates where you update at each time step. And because we have an exploring policy that behaves in this way, in the limit of infinite exploration, we can guarantee that it converges to the optimal solution. Yeah?
So, in the blackjack problem, how does this map? The episode and the time step, what are they in the blackjack problem?
So in the blackjack problem, an episode is defined by a game. You start a game, and then once the game is finished, then this is the end of the episode. You get the reward. And the time step is actually every action that you perform, whether you decide to hit or stick. Of course, if you stick, then the episode is finished, but you can hit several times.
So at every action that we are taking, we are updating the...
Exactly. That's the main difference. Now, maybe in the blackjack it's not a good problem because there are only a short sequence of decisions. But if you are, for example, navigating a robot in a big environment or making some decision task that require a longer sequence of decisions, that might have more effect than in the blackjack case. Any other question? So let's see an example. So also taken from Rich Sutton's book. So this is the windy grid world. Okay, and in this grid world we have an agent that starts at initial location S, starting point, and there's a goal state here G. And these are the moves of the agent. So at each time step we can make an action of going up, down, left, right, and then the agent ends up with the desired cell with some probability. So the thing here is that at every time step that the agent performs some action, then it gets a penalty, a reward of -1. Okay, so every time it's advancing in one of the possible directions, there's some penalty there. So this is the reward of -1 per time step until the goal is reached. Okay, so the idea here is to minimize the number of penalties. So we want to find the shortest route to the goal. But there's a problem here. So there is this upward wind here, which basically brings up the agent to higher positions, right? So if we are here, then we will always be one position higher, and if we are here, then the wind is stronger, and we will go two positions up. So this makes the problem more difficult in the sense that the shortest path, it won't be the optimal because it's not achievable because of the wind. So this is an example, no? So in this case we don't use discounting, and I can ask you now, what do you think that SARSA will do in this example? So what do you think that is the optimal policy if we have this wind going upwards? So notice here that there's a limit. Okay, I cannot go down beyond this point. Any ideas? So will I go here down and then up, or straight and then? So we can run SARSA, and let's see what happens. So this is in turn the policy that is found, and this is the optimal policy, which consists on going straight and then take a round and reach the goal from the other side. Okay, so this is actually the optimal policy that, because of the wind, doesn't find the shortest path by using this optimal. And this is actually what you observe if you plot the number of episodes as a function of time steps that are finished. So these are episodes finished. Now you see that in the beginning, in the first 2,000 episodes, in the first 2,000 time step, then the episode is not finished. So the agent is just wandering randomly around with no updates. Okay, nothing happens. It's brought by the wind upwards, and then it goes back, and it's just a random walk with this deviation here, until we find the goal, because somehow it manages to pass this wind barrier. But notice that once the agent finds the goal, then the progress is very fast. And this is very typical of on-policy learning methods. So once an episode is finished, then the agent can update all these values of these state actions here, and then proceed backwards, and then the number of episodes that are finished increases very, very, very rapidly. Okay, is that clear how this performs? So we can learn, once we reach the goal, then all this learn gets propagated as we make more and more episodes until the point that we reach this fixed point, which is actually the optimal policy in this case. So can we do better? Yes, we can do better. And we can apply here the same techniques that Anders was also presenting yesterday. So notice here that we have done steps that, well, these are like the Bellman updates. Now we look at our guess at the next time step, but we could also be more general. No, instead of considering only our estimate of the next state, which can be very biased in the beginning, we can consider our estimates 2 steps ahead. And this is the idea underlying this n-step SARSA. So this is a global picture of how can we interpolate, let's say, between Monte Carlo control, in which we use a whole trace, a whole trajectory to perform our updates, or the SARSA that you saw before, where we use one-step update. In principle, the ones that uses the whole episode will be non-biased, because it will not bootstrap. It will not use estimates to update our estimates. And on the other hand, the SARSA approach that we just saw, it will perform more updates, but this will be more biased, because our estimates will influence more our updates. So you can interpolate between these 2 ideas by just looking at several time steps in the future. So, and this is the idea of this n-step SARSA method. So this would be the very simple case where we just look 1 step in the future. Okay, so now we define this type of return as the one that we can get at time t plus 1, and we use the estimate from the next time step. But we can look 2 time steps in the future. So here we look at rt plus 1 plus gamma rt plus 2 should be here. There's a typo. Plus gamma square to our guess from so on. And in general, if we take n to infinity, we recover the Monte Carlo update. Is that clear? So we're going to define more general this type of sum as GTN, and this will just use the real rewards until step n t plus n minus 1, and then consider the estimate from which we are bootstrapping from t plus n and on. So this is this Q-value function. And in this way, we can talk about more general temporal difference learning. Okay, so this is what we do now. So instead of using 1 look ahead, we do an n-step look ahead. And the way we define our SARSA updates, instead of considering just our immediate reward by looking 1 step in the future, as we do here, we're going to take this more general n-step return, g of tn. This is going to be our new target now. So, so how can we deal with different episodic, different lengths of episodes? So we can normalize this idea, and we can use this general setting, which we call Sarsa lambda. And in this case, by renormalizing all these factors, we can get something that is between 0 and 1. And in the case of being 0, then we get the one TD update, the one-step TD update. And in the case where it's 1, then we get the Monte Carlo. So this is the way we do it. So we define this weight, 1 minus lambda, and when we take this sum until infinity of all the returns. And we define the equivalent update as the n-step Sarsa in function as a function of lambda. So this is going to be our Sarsa lambda update, which is actually the same as before, but normalized between 0 and 1. So the idea here is that we are interpolating between Monte Carlo and just TD0 updates. And one way to make, so here, there's a problem here, right? You see that there is this infinite sum. And if we want to do an update at each time step, well, that doesn't make, it's a bit of problematic, no? If we need to perform this sum in order to do our update at every single time step, that's just not possible. So this is the idea behind the motivation behind using eligibility traces. So as you saw yesterday, these eligibility traces, it's a some auxiliary vector in the case that we were talking yesterday, which we use to store the relevance, how relevant was this state action visit or this state visit yesterday, in order to describe the value that the reward that we are getting. So in order to identify the states and actions of our trajectory. So in this case, instead of using eligibility traces that involve just the states, as we did yesterday, we're going to consider eligibility traces defined on pairs action states. Okay, remember we want to be model free, so we need to use Q values. And in this case, if we want to store these eligibility traces, we will need another table, another matrix that, in addition to the Q value, it will store the Z values that will actually take care of the states that we are visiting in the most frequently. So this is how these eligibility traces are updated. In the beginning, they are initialized at 0, and then as soon as we visit a state at some time, SA, so it will be 1. And then at each step, when we are going to decrease all the pairs state action. Okay, so this is an update that we do for all possible states every time we move or every time we perform some action. So notice here that this affects all states and actions. So once we have this eligibility trace Z, we're going to use it in combination with the TD error that we just saw before. And in that way, we can perform all these single-step updates without the requirement of performing this infinite sum. This sum here. So is this clear? More or less. We have, this is again our TD error, which is the same as before, but we weight here this TD error by Z, which is the eligibility trace. So this is Sarsa lambda, which is a generalization of the Sarsa algorithm that you saw before. And in this case, it works with traces. So we start with all traces equal 0. We initialize our action values, and we start running episodes. So we take action A, observe a new reward, a new state, and we choose action A prime from the new state using our Epsilon greedy or some exploratory policy. And then we compute the TD error using this formula. We update the trace for those state action pair that we are visiting at this moment. And then notice here this loop. So this is a big and costly loop. So it needs to explore again all possible states and actions. and it needs to update the traces and the values of each state and action. And we iterate this until we find a terminal state. Then we can start again. Any questions? So let's recap a bit the idea. We started with a Monte Carlo method that required exploring starts and performing updates of our estimates of the value at the end of each episode. From that, we incorporated this randomness in the initial state in the policy using this GLIE condition. And then we improve on that by using updates after we finish one episode. Okay, this is Monte Carlo control. And then from that, we introduce all this improvement of temporal difference in which we bootstrap. Instead of waiting until the end of the episode, we perform updates at each time step. And we generalize this idea by introducing eligibility traces so we can interpolate between Monte Carlo and TD learning. So in principle, you would think, okay, what is the best choice of lambda? So theoretically, using a lambda equal, so using the Monte Carlo sample will be the best because it will be the less biased option. However, this will have high variance. So this is the problem with using Monte Carlo. And in practice, it's good to bootstrap. So there's less variance, but then we introduce bias. So there is this trade-off. And if you make this plot of the value of the optimal policy as a function of lambda, you will see that there's a minimum in different, which is not 0 or 1. So this is just to illustrate how this Sarsa lambda works. And this is a very simple grid world. So we have an agent that starts here, initial state, and this is the goal state. And this is an example that illustrates how these Sarsa updates are performed. So what you see here is an example of a path that starts from the initial state and reaches the goal. Okay, there's some randomness here. So this is a random trajectory. And if we don't do if we don't use eligibility traces, what's going to happen? Well, once we find the goal, we're going to update our previous step. Okay, and then the update is not going to propagate more than the last time step. However, if we use eligibility traces, notice that we are going to update all state action pairs, and we're going to weight by how responsible we're in this trajectory that we just made. So what you see here, the length of these arrows is the weight of these eligibility trace. So for the states that we're taking in the beginning, this will be small. And for the states taken at the end, it will be large. So the way this works is that the agent will move here. We will try to perform updates, but all these updates will be 0 because we don't get any reward. And by the time that we reach the goal, suddenly all these states that you see here will be updated. And this is different than in the other case, where there was only one single update. Okay, so here you can see the benefit of using, yes? Sorry, can you repeat the question?
In the first figure, you respected the action direction, and then if you ever move left, you move up.
In this figure?
Yeah, the first one.
Yeah, so this is an example of trajectory. This is one possible trajectory that brings you from here to here. It's just to illustrate how the updates of it's not executing basically all the steps here. So this is for a given path that eventually the agent found the goal state. Let's describe how the updates work for that path. That's what this example is. Okay. Any other question? So what is the problem here? Why cannot we apply this algorithm directly to real-world problems? Well, you saw a bit already yesterday that in reality we have problems that involve maybe continuous variables, continuous actions, continuous space, or even without being continuous, the number of state action pairs is huge, increases exponentially with the number of dimensions of our problem. So in practice, we are forced to use some type of approximation. And this is the idea of using this SARSA algorithm with function approximation. We can extend this algorithm by putting a function approximator for the value function, like for example a linear combination of features, or a nonlinear function approximation. And in this case, well, you can see that it doesn't change much. So instead of having our target, which is defined as a table, we will have here a function. So now it's called q hat, which depends on some parameters theta. And we will define here the new target in this way. So for a given estimate q hat, which is our function approximation, we will consider as target the reward that we observe at the next time step, plus, so this would be SARSA 0, so TD 0. And here notice that the target also depends on our approximation. So this is a bit strange, no? Because we are ignoring the dependence on the target on our parameters theta. But so this is how, so this actually, people try to also optimize the parameters of this target, but this is not very natural because you want to the information flow backwards. So you cannot update your target based on your parameters. So this we consider fixed, and this is going to be our target. And in the case of, for example, linear function approximation, then the update is very easy. We just take the standard gradient, and this leads to the following. So this is the general case, right? We have a new target, which is this one. And then we perform some update in the direction of the gradient. We apply some learning, some step size, and then we compute the gradient of our function approximation. So it turns out that in on-policy learning algorithms like the SARSA that we just saw, these algorithms converge very well in practice once we use function approximation. So if we use linear function approximation, you can show theoretically that it converges in the prediction problem. So if you want just to estimate the value function, you can prove convergence. And if you try to apply this method in a control where you're optimizing the policy, well, you can basically show that it does not diverge. So it might oscillate in a region which is near the optimal policy, but in general, this is giving good empirical results. So in most of the cases, even if you use non-general function approximation like neural networks, it turns out to give good results. Okay, so until now, I explained this idea of on-policy learning methods, where we are trying to learn and estimate the policy that we are using for sampling. Okay, so we are updating the policy that we are using for generating our actions and states. Yes?
So how important the fact that the task is going to be solved for all this, using Monte Carlo?
Yeah, you can also extend these methods for non-episodic cases. You need to do some minor things, but there are variants of that. I just focus on this because it's the most natural. But for continuous settings, you can think about maximum time length and then work on that. Yeah, maybe if you use discounting there are not, but in principle it's not a problem. So let's look now at all these off-policy learning methods. So I motivated before this idea that maybe it might be interesting to update a different policy than the one that we are using for generating the samples. This might sound a bit weird in the beginning, but it's actually very useful. So how are these defined? So now we have two types of policy. We have the policy mu, which is our behavioral policy. That is the one that we use for experiencing with the environment. Could be our Epsilon greedy policy. But we want to find some other policy. Okay. maybe the optimal policy, maybe another type of policy. And the idea here is that we can use a target policy, for example, like is greedy for a current state action value, and some behavioral policy which explores more. Okay, so decoupling these two types of policy, it can be useful, for example, in tasks where we want to learn optimal policies by looking at other agents. So we can see other agents performing some task in some environment, and these transitions between states and these policies we can use to update some other policy. But it also can be used if imagine that I have a batch of data of some transitions that I used at some moment in the past using an old policy, and I want to learn I want to reuse these experiences to learn a different policy for a different task. So off-policy methods will allow us to do that. And okay, so this is the example that I already mentioned before. Imagine that we want to learn the optimal policy while following an exploratory one. Or even if we consider this idea of options where we have several goals, like for example navigating, and then different goals can be go to different corners of a maze. We can by having only one behavioral policy, we can learn about how to reach the fastest way to these other different goals at the same time. So if we can perform off-policy learning, this is something very powerful. And we're going to follow more or less the same structure that we follow with the on-policy method. So we start basically by considering the Monte Carlo updates, and then we'll switch to TD learning again. So the idea behind using sampling and off-policy learning methods is actually very related with this idea of importance sampling. So importance sampling, this is a general idea that is used to estimate expectation of different distributions that the one used for sampling, right? And here you can see, so this is an expectation that I take as a function for this function, f. So imagine that I want to compute this expectation with respect to probability p. So I can generate samples from other distribution, in particular q, and by reweighting these samples, I can get an unbiased estimate of my goal, of the thing that I want to take expectation. So you can here multiply and divide by the same quantity, and then now taking this expectation over q and defining the new expectation as this. So this is called the importance sampling ratio, which just measures the ratio between the the probability I want to take the expectation divided by the probability I'm using for sampling. Okay, so this is the idea behind importance sampling. I can take samples from some distribution and take expectations from another distribution by multiplying by this ratio. So the good thing of this is that I can do that. The bad thing is that, well, it has large variance. So if I use a very bad candidate for Q, I may end up in weights that are very, very close to zero. So these are not relevant. So a naive way of applying this idea in off-policy learning, which is actually the one that we're going to see now, is, for example, so we do these trajectories using pi, and now we have, so this is the distribution of a trajectory. Okay, so we start at some time, and then we have a policy pi, and we can compute this. Let's say this. This is the distribution. Notice here that the model is here, right? Here, this is telling the probability of going to the next state given the time state as an action A. So now I can compute the importance sampling weight. So this is actually the ratio between the policy the target policy that I want to learn about, and our behavior policy, mu. So I take these ratios over the whole sequence of steps. And in that way, I will get some estimate of the reward from the target policy by sampling from mu. Okay, so this is a well-defined update in the sense that it's not biased. But the problem you can start seeing here. So if these importance weights are very small, in problems that require a large number of decision steps, they will rapidly shrink to 0. So in practice, this is not used. Okay. And the idea here is that there's a requirement for this to work, which is called this coverage condition. So the idea is that every action taken on the target policy that we want to approximate has to be visited at least occasionally under our behavioral policy. And this is actually a very strong assumption. It actually tells you that basically your behavior policy needs to be like the optimal policy. And this is a circular argument. So one way of doing that, of improving on that, is using TD targets. So instead of waiting until the end of the episode and use the entire trace and multiply all the importance weights, we can do, again, bootstrapping, right? So we can define the weight of a TD target by importance sampling. And this is this idea. So in this case, instead of multiplying all the corrections, we are going to perform an update by just multiplying a single correction. And this is how this update looks like. So this is exactly the same as we saw before, right? We have this would be our TD target. But now we're going to multiply it here with a weight, with the importance weight. And this will be the ratio between our target policy and our behavior policy. Okay, so now I will ask you a question. So why is this model free? Maybe I can go back some slide. So why can't we do that in a model free? I mean, remember that the probability of a trajectory requires the model to be calculated. It's a very simple answer. Any ideas? Yeah, so once I take the ratio, I don't need to consider the model anymore because this piece simplifies. And actually, I don't need to have the whole normalized probability distribution. If I just have the numerator without the normalizing constant, I can do that well. And this with Boltzmann policies is very easy to do because you just take this ratio. Okay, so what happens, bootstrapping has much less variance than pure off-policy Monte Carlo. But of course introduces more bias because we are doing this one look ahead update. So policies need to be similar only over a single time step instead of the entire trajectories, as we did before in the previous slide. Let's motivate a bit Q-learning, which will be the off-policy learning algorithm that we'll see before the end. And you can have a motivation in the following way by considering these ideas of having this behavior policy and the target policy. So in this case, we won't do any importance sampling, but we will just the Bellman update. So we have two policies now again. Let's consider the behavior policy mu, and from this one we will draw an action, AT plus 1. And then we're going to consider an alternative successor action, which would be drawn from pi. So here we have a state ST, and we will consider two possible actions. The ones from our behavior policy, mu, and the one from our target policy that we are trying to learn. And this is A prime. So this is our update. Instead of using our behavior, the action that we chose from our behavior policy, we're going to choose A prime, which is taken by the target policy. And the update in our Q values is going to be towards this alternative action. So here we have A prime. What is Q-learning doing? Well, Q-learning is a particular choice of A prime. And this particular choice is that this is the greedy action, according to our current estimate of Q. So if we take the greedy action with respect to pi, okay, we take the argmax here, then we end up with a non-Q-learning algorithm. So Q-learning is a particular idea of this off-policy learning that doesn't use sampling. And this is actually the real algorithm. So we first initialize our array of state actions arbitrarily. Then we choose an action, for example, being epsilon greedy. This is going to be our behavior policy, mu. And at each time step, we perform this update. So in this case, our target is going to be the maximum, the maximum over the next state action values. Okay, so this is an off-policy learning algorithm. This is Q-learning. And you can see here the backup diagram. So instead of looking just one possible time step in the future for one transition, we take the maximum over all possible next action pairs. So going back, this is actually the Bellman optimality operator. And we can reduce the step size over time. And actually for Q-learning, this is more necessary in practice. So the convergence properties, so for appropriate choice of 4, Q converges to the optimal action value, and the greedy policy to an optimal policy. So far, this is the tabular case. I will explain now what happens when we go to the function approximation case. But I think it's interesting to use this example, also from Rich Sutton, that explains this difference between SARSA and Q-learning. So remember, SARSA was an on-policy learning algorithm that finds the optimal policy and learns a policy from samples and experiences from the behavior policy. And we have an off-policy algorithm that tries to approximate the target policy, that tries to learn it from experiences with a different policy. And this is a nice illustration that how both can give rise to different solutions. So this is, again, a grid world. We are considering tabular case. And here we have a source state where the agent starts and a goal state here. And there's a cliff. So if the agent reaches one of these states in the gray zone, it will be automatically transported to the starting state, and it will pay a penalty of -100. So it has a high cost to reach the cliff. Basically kills the agent and sends it back to the starting point. Otherwise, if the agent doesn't fall the cliff, then it gets a reward of -1. So every time, every step takes a cost of 1 unit. Now we can differentiate two paths here. The safe path that goes upwards and then down to the goal that tries to avoid the cliff, and then the optimal path, optimal in the sense that is the shortest path from the starting point to the goal. And maybe from your intuition at what you learned from the previous time, you can make a guess of how these different algorithms will perform. So does anybody of you have a guess of what will be the difference between Q-learning and SARSA in this particular example? Okay, so let's look at the solution. So this is if I run both Q-learning and SARSA, then I get these results. Okay, now notice that SARSA is going to find so this is the sum of rewards during episode, and we see that SARSA obtains higher rewards, and Q-learning obtains lower rewards. So why is that? If Q-learning is approximating the real optimal policy. Well, it turns out that it finds the shortest path, but it's a more risky policy, the one that is using for exploring. Okay, so Q-learning will try to explore these areas more because these are more promising, they are shorter to the goal, and then the agent will fall off more frequently to the cliff. Whereas the SARSA algorithm will learn the longer route, but the safer one. So overall, the average reward that SARSA will find will be higher. And this is something illustrated. This is something that illustrates this difference between on-policy and off-policy methods. So off-policy methods usually find the optimal solution, but their policies are perform worse sometimes, like in this case. So how can we extend Q-learning with function approximation? We can do the same as we did with SARSA. So we again consider the objective. based on the Bellman optimality equation now instead of the Bellman evaluation. And in this case, we have this maximum here. We again replace our Q function by an estimate of it. So instead of having Q, we have Q hat, which is parameterized by theta. And we do exactly the same idea. So we have parameters theta, we can do gradient descent, and we can update the parameters of our function approximator according to the gradient descent rule. So this allows us to use Q-learning in a much higher dimensional spaces, and we don't need to store all the state action pairs. So I'm going to summarize what we have seen today. I've shown you how you can do on-policy and off-policy control. How can you compute these optimal policies? That it goes beyond function evaluation of a policy. And we have seen this difference idea between doing Monte Carlo, which is non-biased but has higher variance, and it requires finish an episode before performing updates, versus bootstrapping, which is biased, but it has less variance for control computation. And then we have seen two algorithms that are widely used in the literature that hopefully you can use in your research. So one is SARSA, which is an on-policy control method, and one is Q-learning, which is off-policy. So in the first case, we are trying to learn a policy that we are using to generate our samples. And in Q-learning, we are trying to learn or approximate a target policy that is different than the one that we are using to generate our samples. And we have seen that when we cannot enumerate the state action space, we can do function approximation by using some gradient descent. So I didn't go much into the details of this, and I didn't touch many other topics. So this is, as you know, an area of research which is very active. So maybe I can say a few things about these two other approaches. So this idea between, so what we have seen so far, let's say that is a value-based approaches. So we are focusing on the value function, and we are trying to find optimal policies by having this value function either stored as or action value function, either stored as in tables, in memory, or either using function approximation. But there is also a whole range of methods, policy-based, also called actor-critic methods, that they actually perform updates on the policy without requiring storing the value function. So there's also another type of methods which are non-model free. So if I have a model of the environment, why not using that model to generate samples and learn faster from that? So maybe I can say a few words about these two ideas before we end. So in these policy-based methods, why are interesting? Well, in many problems, the policy is simpler sometimes than the value function. So the value function can be very complicated, but the policy can be very simple. It can be just take one action and that's it. And now it turns out that in many problems, also the policy that you want to learn is a stochastic. So think about, for example, poker, when you have partial information or you have an adversary. And in that case, the optimal thing to do is not to do always the maximal, the action that is giving maximum value. So you need to change. So in that case, you are required to use a stochastic policy. And then it's important, for example, also in robotics, when you are trying to teach a robot to learn something, that your policy changes are smooth. So that the robot is seeing things that have seen in the past, and so it doesn't make things that can break it. So enabling smooth changes is better done, is easier done if you use a policy-based method instead of a value-based method. So these are other reasons to better relate to biology. In neuroscience, these are more naturally based methods. And also, well, I was also giving you a glimpse of this model-based reinforcement learning. Now, what we have done so far, you saw that because we are using state action values, and because in the importance sampling we could simplify this using these ranges, we don't need to have a model of the environment. And this is actually very useful if we want just to deploy our agent in an environment and learn from it. But if we have a model, we can exploit it. So if we have a model of the environment by, for example, and approximating this transition probability and the reward function, then we can use it to generate simulated trajectories. So think about, for example, table games where the model is very simple. It's just the rules of the game of chess or Go. So these are simple models that you can know in advance, and from that you don't need to interact with the real world. You can do simulation, you can simulate trajectories, and this you can do it much higher large scale and learn from it. So in particular, we can apply reinforcement learning methods to these simulated trajectories as if they had really happened to learn out the action value function and the policies. And moreover, we don't need to just do model-based reinforcement learning. We can combine two things. We can interact with the environment and at the same time have a model which we are updating based on our experiences. So this is a bit more complicated because it introduces an extra source of error. Of course, if you're approximating the model, you can make more errors, so we have to add additional possibilities of making mistakes. So if there's a model mismatch between the model that you are learning and the reality, it can be problematic. And I think I'm done here, so I take questions. A bit earlier.
Well, I'm one.
Yes.
First of all, can you explain better to me, because I didn't get perfectly why SARSA is performing better than Q-learning if Q-learning is converging to the optimal goal?
So maybe this So this example illustrates that very well. So here in the case of Q-learning, we are taking the maximum of our x. So this means that in this case, since we are only optimizing the distance from the starting point to the goal, the optimal value will be the shortest path. So these cells here will be visited more frequently because they lead to shortest path. Now, in the case of SARSA, maybe Anders can.
Another reason is that if Q-learning falls off the cliff, that will not be updated in the previous state, because the previous state will consider the best thing that would have happened.
Yeah, exactly.
Right? But SARSA, when you update and it falls off the cliff, it will use that negative reward to update the previous state. So Q-learning lives in this kind of optimistic world where it thinks that the best possible action I could have taken is the one I should have done, and then that's the one I use for my update. That causes Q-learning it doesn't get this experience, accumulate this experience of falling off the cliff being a bad thing in the Q-learning.
If we wait many more episodes.
Right, so if you turn off exploration and the actions are deterministic, of course, the optimal path will eventually be
I
higher.
should have the exploration decay, right? So if the next slide, so if we applied this decay in exploration and if we wait much longer, eventually it will go up there, no? You would expect that.
I would expect that to be.
Yeah.
And how much does it, since we are learning from some other policy, right, does that depend on no policy, so we are learning from a different policy.
Yeah.
So that different, how do you choose that?
Well, this is actually this choice, no? If you have you have these estimates of the Q function. So taking the maximum over the next time state, that's going to be a choice for your target.
It's off policy in the sense you don't update based on the action that you actually took. You update based on the action that you think is the best one.
In the cases where the reward is after an episode, it completes.
Mhm.
So can you explain again how the update again is done? So we are taking every action based on we are doing the update based on the immediate reward, but the reward is at the end of the episode. So how do we actually propagate it? We propagate it back.
Yeah, so in these cases where you don't receive any reward or punishment during your evolution until you reach a goal, well, then nothing happens until you reach that goal for the first time. And then you start propagating all these rewards backwards.
So we take that reward for every time step, for every action that we took, we take.
Yeah, so that depends on if you use, on the type of update that you use. If you use, for example, eligibility traces, once you reach the goal, you will update all your trajectory that led to that goal. But if you're not using these eligibility traces, you will just update the last value. And then it will take more time to converge.
So, but how do we choose the actions based on the immediate reward then? For every time step, how do we update that?
Well, that depends on the algorithm. In the case of Q-learning, you will take the maximum of your next, of the actions of your next state. And in the case of SARSA, you will take a different choice. You will just take, your target will be your next estimate. So this is the idea behind the two type of Bellman equations. No, in this case, this would be the one corresponding to SARSA, and this would be the one corresponding to.
Just to take an example, yesterday's example, blackjack.
Yeah.
So the reward is at the end of the game. So every action, what immediate reward do we assume for that?
Well, in this case, we don't have any immediate reward until the end of the episode.
So in the, suppose the cleft.
And in the cliff example, yeah, you get a reward of -1 at each time step. So in that way, you can actually start performing. If you initialize with 0, you can perform, can convert.
So giving -1 for each time step causes the optimal policy to try to reach the terminating state as quickly as possible.
So every time so we lose.
Yeah, that's the difference. Because longer trajectories will be penalized more.
According to the fact that Q-learning is trying to learn the optimal path, alpha parameter should be more, should have an effect more.
Yeah. Yeah, so it's more sensitive to this parameter than the on-policy methods. On-policy methods are not that sensitive to this parameter.
Right. The reason it becomes sensitive is because when one Q value becomes higher than another one, that affects what you do. So when you're just estimating, your policy is fixed. So you're just estimating. But here, two large updates might